You may have noticed that so far we've been assuming that we can put 2 electrons in every orbital, just like you learned in general chemistry. The reason for this has to do with the indistinguishability of electrons. I can't tell them apart, and the fact that electrons have a spin of 1/2, which leads to the fact that they need to have wave functions that are antisymmetric. So we need to talk about both of these concepts, indistinguishability of electrons and antisymmetric wave functions, in order to understand the Pauli exclusion principle and Hund's rule that you learned in general chemistry. The concept of indistinguishability is just the idea that I can't tell one electron from another. They're all exactly the same. So if I have an electron configuration where I have one electron in a 1s and another electron in a 2s orbital, so I'll use these parentheses to label the electron. So this labels the electron. This is electron number 1, and this is electron number 2 to keep track of which electron is in which orbital. That configuration has to lead to exactly the same results as if I have electron 2 in 1s and electron 1 in 2s, because I can't tell which electron is which. I can't tell which electron is in which orbital. And so I need to write wave functions or electron configurations in such a way that I can't tell which electron is in which orbital. So we typically define a exchange operator. So p hat is going to be our exchange operator. And all this operator does is to switch the labels on my electrons. So if I operate p hat on the wave function 1s with electron 1 in 1s and 2s electron 2 in 2s, the result of that operation is equal to 1s with electron 2 and 2s with electron 1. And because this wave function is not the same as this wave function, it doesn't look exactly the same, this wave function is not an eigenfunction of this exchange operator. And all of my wave functions have to be eigenfunctions of the exchange operator. So for instance, if I had both electrons in the 1s orbital, so I had 1s1 and 1s2, both electrons are in the 1s orbital, and I operate p hat on that wave function, I will end up with 1s2, 1s1, and that would be exactly the same because it wouldn't matter whether I wrote 1s2 first or 1s1 first. Those are the exact same orbital. The electrons are in those exact same orbitals, and I can't tell the difference between this configuration and this configuration. So here, our wave function is not an eigenfunction, and in this example where I have both electrons in 1s, this is an eigenfunction of the exchange operator. So in order to write this wave function where I have one electron in 1s and one electron in 2s as an eigenfunction of the exchange operator, I could write linear combinations of that. So I could write 1s1, 2s2 plus 1s2, 2s1, or 1s1, 2s2 minus 1s2, 2s1. So these two superposition states, or linear combinations of the wave function, would be eigenfunctions of the exchange operator. So if I now operate p hat on 1s1, 2s2 plus 1s2, 2s1, and I just exchange the labels, I end up with 1s2, 2s1 plus 1s1, 2s2. And you can see that because addition is commutative, this is exactly the same as this. And so my eigenvalue for this combination is +1. If I operate on the wave function where I've subtracted the two possible configurations of which electron is in which orbital, then I will end up with an eigenvalue of -1. So here we've operated the exchange operator on the linear combination where we've subtracted the two possibilities. And when we exchange the labels, this term becomes this term, and this term becomes this term. And so if I pull a minus sign out, just factor a minus sign out of that, then I can see that this wave function is the opposite, the negative, of my original wave function, and so the eigenvalue for that is -1. So in order to make sure that wave functions are indistinguishable, we have to make sure that when we operate the exchange operator on our wave function, that we get either plus or minus the wave function back again. When the eigenvalue is +1, we say that the wave function is symmetric to exchange. And when the eigenvalue is -1, we say that the wave function is anti-symmetric. In general chemistry, we talked about electrons as being spin up or spin down. And we defined this extra quantum number called the electron spin quantum number, which could be +0.5 or -0.5. And this was just something that we told you was true about electrons. But let's talk a little bit about where that comes from. So it turns out that an electron in a magnetic field will behave as though it has a magnetic moment. So we know experimentally that electrons have a magnetic moment. So they will be attracted differently to the poles of a magnet depending on what their characteristics are, whether they're +0.5 or -0.5. And the fact that a charged particle has a magnetic moment means that it must have an angular momentum associated with it. And so this electron, one of its properties, intrinsic properties, so just something that is part of that electron, is the fact that it has an angular momentum associated with it. Now, it turns out that this angular momentum is not really related to the electron spinning on its axis, but rather is a relativistic effect. And so if we formulate our quantum mechanic model and include relativity in that model, we will naturally get a new quantum number, which is called the spin quantum number for the electrons. So let's use sigma to designate our spin wave function for the electron. So we can separate out the spatial wave function, psi, that we've been talking about up until now, which tells us about where the electron is in space, r, theta, and phi. And sigma is going to be our spin wave function. So we know that we have this spin angular momentum, so we can define a spin angular momentum operator just like we have a spatial angular momentum operator. And remember that if we operate the spatial angular momentum operator squared on our wave function, we get h bar squared L times L plus 1 times the wave function back again, where L is our angular momentum quantum number for the spatial wave functions. So in the same way, when we operate the spin operator squared on our spin wave function, we're going to get S times S plus 1 times h bar squared times our spin wave function back again. So these this intrinsic angular momentum of the electron works in exactly the same way that the spatial angular momentum operators work. And because angular momentum is a vector, it has a direction as well as a magnitude. And the direction is represented by m sub s, just like our direction of our angular momentum operator in space, we have m sub l. And remember that m sub l can go from minus l up to 0 up to plus l in integer steps. The same thing is true about m sub s. It can go from minus s up to 0 up to plus s in integer steps. So it turns out that for electrons, s is always 1/2. That's the only value of that quantum number that works for electrons. And so all electrons have an s quantum number of 1/2. That means that m sub s starts at minus 1/2, add 1 to that, we get plus 1/2, and then we're at the end of our series, we're at plus s. So the only values for m sub s are minus 1/2 and plus 1/2. So we usually say that minus 1/2 is spin down, and we represent that with the wave function beta. Plus 1/2 is spin up, and we're going to represent that with the wave function alpha. Let's complete this picture by thinking about the analogy to our vector diagrams for the orbital angular momentum. Remember that the wave functions, the spatial wave functions that we've been talking about, are eigenfunctions of the LZ operator as well as eigenfunctions of the L squared operator. And so we know the length of this vector, the magnitude, because we know the eigenvalue for the L squared operator, and we know the possible directions of this vector because we know the shadow on the z-axis. We know that LZ eigenfunction. So if L is equal to 1, LZ is equal to 1 times h bar. So in units of h bar, the shadow on the z-axis can be 1, or it can be 0, or it can be minus 1. And so I have 3 possible directions for my vector. All of those vectors have a length of square root of 2 h bar because they all have the length L times the quantity L plus 1 square root times h bar. And so L plus 1 plus 1 is 2, times 1 is 2, square root of that is square root of 2, times h bar is the length of this vector. Now remember that I don't really know anything about the x and y axis. And so the shadow that this vector makes on the x and y axis is unknown. And so I can think about this vector as precessing about the z-axis on this cone. Same thing with the -1 direction and the 0 direction. So in analogy to that, my spin angular momentum for my electron has the same properties. Those wave functions are eigenfunctions of the S sub z operator, which tells me the shadow on the z-axis. So when I operate SZ operator on alpha, I get 1/2 h bar alpha back again. So I get the m sub s value. So remember for alpha, m sub s is plus 1/2. So I get m sub s times h bar times the wave function back again. And when I operate the SZ operator on the beta wave function, I get minus 1/2 h bar times beta back again. And so my eigenvalue for the z direction is just m sub s times h bar. And my length of my vector, remember that s hat squared on either one of these, alpha or beta, so we'll say sigma is equal to s times s plus 1 times h bar squared times that wave function back again. So if s is equal to 1/2, then we have 1/2 plus 1 is 3/2 times 1/2 is 3/4 h bar squared times sigma. And so the length of this vector is the absolute value of the length of that vector. And this is s squared. And so the length of this vector is square root of 3 over square root of 4, which is 2 times h bar. And again, the L sub x and L sub y operators do not commute with the L sub z or the L squared operator. And so we don't know anything about the shadow on the x and y axes. And so these vectors are precessing about, we can think of them as precessing about the z-axis because we don't know the x and y direction are completely undetermined.